acid-base titration for GCSE, iGCSE and general chemistry. We will start with a review of neutralisation reactions, that's acid-base reactions. Then look at titration methods, then some model calculations using titration data, and then for those doing iGCSE, details of indicator chemistry. Neutralisation are reactions between acids and bases that form a salt and water. So acid and base goes to salt and water. Bases, metal oxides and metal hydroxides, are classified as bases in that they react with an acid to form a salt and water. For example, copper oxide. However, there is a subgroup of bases that are soluble in water, and they are both bases and alkali. So an alkali is a soluble base. For example, sodium hydroxide. Sodium hydroxide reacts with an acid. It is a base to form a salt and water. There is a third group of compounds that react with acids, metal carbonates, forming salt, water and carbon dioxide following this general word equation. AQA classifies the reaction with metal carbonates as a neutralisation as well. Let's look at some examples. The reaction of hydrochloric acid with base alkali and also of metal carbonate. Metal oxide, for example, copper oxide, reacts with two hydrogen chlorides or hydrochloric acids. Could you complete that equation? Pause, complete the equation. Go on to complete the reaction with sodium hydroxide equation and the reaction with copper carbonate equation. Take your time, come back when you have answers to check. Okay, so to reveal, CuCl2, that's copper chloride, 2 chloride ions with 1 copper, and water, so salt and water. Hopefully you have the second equation ready. Sodium hydroxide, NaOH, HCl, sodium chloride, the salt, and water, a 1-to-1 reacting ratio. Metal carbonate, copper chloride, the formula of copper chloride is always CuCl2. Carbon dioxide and water following the general word equation, but to balance we need 2 HCl. Some more problems, the reaction with sulfuric acid. So we have an alkali, sodium hydroxide. I've given you the balanced reactants. Metal oxide, sodium oxide, the balanced reactants, and then ammonia, which has a slightly anomalous behavior as a base. So can you complete the products and balance for those 3 neutralizations? Come back when you are ready to check your answers. Okay, so I'm about to reveal. Na2SO4 is sodium sulfate and 2 moles of water. So you'll notice with sodium hydroxide, it's a 2-to-1 reacting ratio. Sulfuric acid has 2 acidic hydrogens. So 2 sodium hydroxides to 1 sulfuric acid, producing 2 moles of water. Metal oxide, again, sodium sulfate does not change its formula. Here we just have the 1 mole of water. And ammonia, anomalous in that if ammonia is written as NH3, as it is, the salt is formed, but there is an absence of water. So with ammonia, we just form the salt. Those equations all need to be able to be reproduced in the context of titration. Moving on to titration methods, which I'll cover as best I can in this format. So having prepared your solution in a volumetric flask, we now need to extract 25 centimeters cubed, the usual volume. You may need a different volume, using a volumetric pipette. So here is our volumetric pipette with pipette filler. I have a traditional image there. You may have a more modern one to use in your laboratory. I hope so. The procedure before you use the pipette is to rinse the pipette with tap water, distilled water, and then a little of the solution that is to fill the pipette. So that's the same procedure as for rinsing the burette. Now, having inserted the pipette into your volumetric flask, you'll notice that there is a graduation mark at the volume printed on the pipette. In this case, I'm assuming it is 25 centimeters cubed. So we're going to fill the pipette up to the graduation mark on the pipette. Obviously, bottom of the meniscus as previously. Having filled the pipette to the graduation mark, you then obviously remove from the standard flask and transferring a short distance to a conical flask, a clean conical flask. Make sure that the conical flask is close to your volumetric flask and you're not transferring that any distance, because we don't want any drops or any loss of solution from the pipette. So my recommendation is that you remove the pipette filler and allow the pipette to drain. Touch the surface of the solution with the pipette and allow the pipette to drain for 10 seconds after it appears to have been completed. You will then see that there is a small volume remaining in the pipette. That is meant to be there. That is part of the design. So the pipette delivers 25 centimeters cubed from the graduation mark to the tip of the pipette, but the small amount of solution held in the pipette is taken into account in measuring that volume. So your pipette, when empty, should have a small amount of solution in the tip. So we have 25 centimeters cubed of a solution of known concentration in the conical flask. We now need to prepare our burette and the burette solution. So the process for preparing the burette is the same as for the volumetric pipette. That is, you rinse the burette with tap water, then with distilled water, then with a little of the solution. We fill the burette from a beaker with shall we say, the solution of unknown concentration. And of course, we need to make sure that the tap of the burette is closed, which is in the position as indicated. We also note that we have a beaker underneath the burette. We do not place the conical flask under the burette at this point because there may be spillage in this part. You often, when you're inexperienced, overfill the funnel and then you have solution running down the burette. So we don't want that going into the conical flask of our test solution. So a beaker to catch any overflow. So here is a burette ready to be used with the solution. That's now been transferred to beneath the burette. There are 3 errors in the setup of this burette. I'd like you to pause the lesson and look carefully at the burette. What are the 3 errors? Come back when you're ready to discuss further. Okay, so I can help the situation by a diagram of the burette in the correct setup. And you'll notice there are 3 distinct differences. Firstly, the filter funnel, or the burette funnel has been removed. The burette funnel often has the potential to drip into the burette during a measurement, which is obviously not desirable. So the burette funnel needs to be removed. You'll notice also a difference here and here. If you look very closely, we must fill below the tap. And finally, the position of the burette tip is within the shaped part of the conical flask. The conical flask is shaped as it is to allow the burette funnel into its mouth. So in this arrangement here, on the left hand side, we can see there's the potential for spillage. There's no such potential on the right hand version. So it's the right hand version that is correct. So we then, having noted the initial volume, we add some indicator, and generally we'll see that there's a color change, and at the color change point we stop the titration and we take the final volume. So the volume delivered by the burette is the difference between the initial and the final, and that is called the titer. So let's move on to some model calculations using titration data. Now the simplest type of titration data is an acid-alkali titration, and in those types of calculations there are 4 variables to consider, and there we've listed them, or I have. We've got the concentration of the alkali to consider, the concentration of the acid, the reacting volume of the alkali, and the reacting volume of the acid. Now, provided we are able to generate a balanced reaction equation, if we have 3 of the variables, that's 3 of this 4, then the 4th can be calculated. So let's look at a model example. Find the concentration of a solution of sodium hydroxide, and the alkali, of course, if 25 centimeters cubed is found to react with 20 centimeters cubed of dilute nitric acid of 0.05 mole per litre concentration. So just looking at this, though it doesn't specifically state it, 25 centimeters cubed would indicate that that has been measured using the volumetric pipette, and 20 centimeters cubed, we would assume that that has been delivered by the burette. So what we first need, of course, is a balanced chemical equation. Sodium hydroxide and nitric acid is not problematical, and of course we've got the mole ratio there, 1 mole to 1 mole. So our first step is to look at our data. What have we got here? What can we use? Well, we've got a volume of acid and a concentration of acid. So it's quite useful sometimes just to link the data, volume and concentration together within the question so that there isn't confusion or an error made. So we can work out the concentration, we can work out the numbers of moles of nitric acid. That's 0.02 times 0.05. That, of course, is concentration times volume. So concentration times volume in decimeters cubed. So the 0.02 comes from 20 centimeters cubed. 20 centimeters cubed is 0.020 decimeters cubed. So our concentration, of course, is already in moles per decimeter cubed. Now, because it's a 1-to-1 mole ratio in the balanced chemical equation, then the moles of sodium hydroxide is equal to the moles of nitric acid. So our moles of nitric acid was found to be 0.001, or 1 times 10 to the minus 3, may be what you find in your calculator, and that is equal to the numbers of moles of sodium hydroxide. So we then simply rearrange this equation. Moles is concentration times volume, so of course concentration will of course be moles divided by volume. So here we've got the numbers of moles, and here's our volume in decimeters cubed, so that gives us our concentration of 0.04 moles per litre. So before rushing on, I'd like to give you a problem to solve yourselves and then to come back and check against my answer. So pause the lesson and complete the problem, which is, I'll just talk you through it, an unknown concentration of sodium hydroxide solution titrated against sulfuric acid, 25 centimeters cubed, and of known concentration 0.100 mole per decimeter cubed. The alkali, that's the sodium hydroxide, was delivered at 24.05 centimeters cubed. So 25 centimeters cubed of acid from the pipette at 0.1, and the burette delivered 24.05 to achieve neutralisation. Can you calculate the concentration of the sodium hydroxide solution? Okay, so let's have a look at my model answer. Well, of course, the first thing is that we need a balanced chemical equation. I hope you've got that correct. 2 sodium hydroxides means it's a 2-to-1 mole ratio. We've got a volume of sulfuric acid, and we've got a concentration of sulfuric acid. Tie those together, so that gives us numbers of moles of sulfuric acid. Volume times concentration, volume in decimeters cubed. We're just using moles is concentration times volume. So what about the moles of sodium hydroxide? Well, it's a 1-to-2 ratio. 1 sulfuric acid requires 2 moles, twice the moles of sodium hydroxide. So to turn 1 into 2, we multiply by 2. So we've got to multiply the moles of sulfuric acid by 2 to achieve the moles of sodium hydroxide. Then, of course, we'd have a volume. We have a volume of alkali at 24.05. So the volume of alkali is 0.0245 decimeters cubed. Our numbers of moles, of course, just comes down from here. So there we have our concentration in moles per decimeter cubed. 3 significant figures. I've got 3 sig fig here, 3 sig fig here, 3 sig fig here, and 4 sig fig here. So we'll go with 3 significant figures for the concentration. So for iGCSE, we need to briefly cover some factual details of the indicators used in titrations. There are 3 indicators you need to know about: litmus, thymolphthalein, and methyl orange. You need to know about their colors in acids and alkali. So litmus, you're probably very familiar with, is red in acid and blue in alkali. Thymolphthalein is colorless in acid, but blue in alkali. Methyl orange is red in acid and yellow in alkali. Those color changes need to be known. The point at which the indicator color changes is called the indicator endpoint. So a typical exam problem would be, what endpoint color change is seen when alkali is added to acid using methyl orange as indicator? Pause, analyze this table and come up with the correct color change. Okay, so, well, in alkali, methyl orange is yellow, so as you add acid to the point or to the indicator endpoint, you will then achieve a red color. For this particular topic, I strongly recommend you attempt any questions in your textbook, for instance, end of chapter questions, but also find some past paper questions. If you don't have them provided for you, I can recommend the Physics and Maths Tutor website or other websites which are equally as good.